Hello, students. We had a question here about group work number 1 and group work number 2. So let's take a look at group work number 1 first, and let me grab a little bit of white space. We'll see what we can find. All right. So we know that these are angle bisectors. Okay, so that means they just cut the angle in half perfectly. And it says if the measures of A and B are known, then the measure of angle D can be found. Explain how. Well, remember, if you know what angle A is, then you know what each of the two smaller pieces are because it just cuts it in half. So really, what you'd end up with is, let's see here, something like the measure of angle A divided by 2, right? That's what this smaller one is. And then we'd add the measure of angle B, but divided by 2. So now that gives us these two components that are inside the triangle. And then plus the measure of angle D. And those all have to add up to 180 degrees, right? So if you were to take the two components you do know about, and which is I know this value because I know how big A is, which means I just cut it in half, and I know this value as well. And so use the properties of equality, bring them to the other side, and you will be able to find the measure of angle D equals 180 minus, and then of course these things are brought to the other side. And that's how you could find the measure of angle D. All right. All right, let's see here. Then B, now it says, okay, so now A and B are not known, but angle C is known. So I know how big this one is up here. Now I would encourage you to try this. Put a number in for C. Okay. I know it seems weird, but just go with me on a journey here, right? Let's just say this is 60 degrees. Okay. Now pick numbers for A and B. Now remember, just has to add up to 180 degrees. So let's just say that this is 40 and this one over here is 80 degrees. Okay. So again, if you knew that this one up here was 60 degrees, someone else could go find these two. Could I find the measure of angle D right here? And maybe it relates back to the 60. So maybe there's a connection, a nice connection where maybe I don't have to know A and B. I could just tell you one angle, and if I knew angle bisectors, you could find the angle right here. So let's take a look and see maybe how we might be able to approach that. Let's take a look. Let's take a look. Okay, so I know angle C. So what do I know? I know the measurement of angle C plus the measurement of angle A plus the measurement of angle B. All of those together is equal to 180 degrees. Okay, so I know that. Now remember, I don't know angle A and angle B, right? But I do know angle C. But use what we found in A. Remember what we found in A? We found that the measure of angle D is equal to 180 minus measure of angle A divided by 2, measurement of angle B divided by 2. And then maybe if we multiply everything by 2, then I'd have 2 times the measurement of angle D equals 360 minus measurement of angle A minus the measurement of angle B. Okay, so there we go. And again, all I did is multiply by 2. If you divide by 2, you get back to the 180 minus half angle A minus half angle B. So why is this so important? What is so big about this? Well, if you do a little bit of algebra here, Like maybe if you bring these pieces, the measure of A and measure B, bring those to the other side. And of course, they were negative on the right, they'll be positive on the left. And then this can move over to the other side and become negative. And the reason why that's kind of a cool idea is down in this next one, I see an A and a B, and I could actually replace those with what I just discovered, which is measure of angle B minus measure a plus that measure of angle A is going to give us 360 minus 2 measurement of angle D. Okay, and that equals 180. And the first part is actually the measurement of angle C. Okay, so let me move that over just a little bit so it lines up. So yeah, that's what all of that work can do. So sometimes you solve a problem, you can actually use it in the next one. And so yeah, I know angle C, so I know this one. Can I find the measurement of angle D? And if you take a look, think about this like we did back in chapter 8. These are basically just variables. So you know this is some variable. You know this is some variable. So go ahead and call those out. And then try to solve to get measurement of angle D all by itself. So that is going to be my big hint on this question. Let's move on to question 2, which is I think this is the triangle folding one. Yeah, this is the group work with triangle folding. And okay, let's see here. Each person should draw a large triangle, doesn't matter the size or shape, and then fold a crease B prime so that A falls on top of A prime. Okay, then unfold it and fold the top along B prime so that B falls on B prime, then fold basically the other two over to create that shape. Okay, that makes sense. Now what's up? Why is B prime perpendicular to AC? All right, let's take a look. Let's see what we've got. Okay, so when you fold this point A and you fold it over onto A prime, and then you create this crease, to be honest, we don't know that it's perfectly 90 degrees. We just know that it exists. Oops, a little too far there. Sorry about that. So now when you unfold it, what I want you to think about is when you had folded it, it made a straight line. When you unfold it, it still makes a straight line because they lined up right on top of each other. So we're using the symmetry out of 11.2. Now that we've got the idea of the symmetry, think about it here. I have an angle right here. Forget about that right angle. I just have an angle and another angle. Okay. Now I know that those angles are actually the same. And they're the same because I folded the piece of paper over itself. So that angle had to be the same on both sides. So what you now know is that x plus x has to equal 180 degrees. And if you solve this to get x by itself, I think that will show you why B prime is actually perpendicular. What theorem does the folded rectangle illustrate? So the folded up rectangle, don't forget again, that's the one way over here. What theorem does it illustrate? So if you take a look, you've got an angle down here, and when you unfold it, it's this angle right there, which is the same as this angle right here. Okay, so there's that angle. And I've now folded it in to make an angle right here. Okay, next up, I've got this angle right next to, I guess, on the other side. Oh, that's not good. I didn't know they did blue. I guess I should have been paying more attention. There we go. And that matches up with this angle C, which matches up with this angle C. Okay. And then I have an angle right between them. I need a different color. What do I have? Orange, I guess. Okay. I have this one in the middle, and when I unfold that one, it shows up at the top up here, which matches because I've folded it down right here, so that matches. And that would be this one way up here at the top. So if you take a look, I have a triangle that has an interior angle that is red, one that is orange, and one that is green. And when we bring them together and put them over here, what we get is an orange, a green, and a red end up making a nice straight line. So this would be the theorem that shows that the interior angles of a triangle is 180 degrees. Now it says the theorem shows that this is a rectangle. And so if you look at this end result over here, yeah, that is going to be a rectangle. So when it says explain why, go back and think about how did you do the folds? Think about what we explained for this first fold. When we fold it over, what kind of an angle do I get down here? And so you have angles that are congruent and supplementary. And you repeat that process. If you think about it, all you're doing really is creating a similar piece right here. You take this one and then you fold it over. And you take this one and you fold it over. And so you're creating these creases the same way you created that first crease. And so when you unfold, what kind of an angle do you have down here? And hopefully you can kind of see why, because of what we already did in the first one. All righty, lastly, what is the length of GF in terms of the length of the base AC? All right, well, GF right here, right? If you look at it, it's the base of the first triangle, and let me get a different color, sorry about that. It's the base of this triangle over here on the right, and half the base of this triangle over here. And so if you think about it, that's half of each of these pieces. Now let me demonstrate kind of what that would represent though. So over here, we have half of this, which is half of AB prime. And then I have half over here as well, which is half of CB prime, which is the same thing as CF. So when you fold things in and if you unfold them, you fold them in and they kind of line up on top of each other, you unfold them, you've got to have twice as much. So AC, whatever that length is, half of that length is GF. And since it's a rectangle, that also means that DE is the same. It is half as big as AC. So there's some of the cool properties of just doing a little bit of paper folding on this one. All right, I hope that gets you in the right direction. Let me know if you have other questions. All right, off you go.